Welcome to the Audio Architect Soundweb London Configuring Logic Part 1 Overview video. So what is logic? A simple explanation can be stated that logic allows for a function to be executed based upon the outcome of a predetermined event. We all exercise some form of logic in our day-to-day lives. Consider setting an alarm. We can write a rule so that when the clock is equal to 7 a.m., the alarm will turn on, indicating that it's time to wake up. BSS Soundweb London devices support a configurable logic system, giving us access to control many parts of a system without having to use resources such as a PC running the Audio Architect venue file, or in some cases, even using third-party control. In the Logic Rules Overview video, we compared the Audio Architect Logic Rules tool to Soundweb London Logic with the following chart. Now, we won't get into all the details again, but as a reminder, Soundweb London Logic allows us to create simple logic circuits such as a push-to-talk microphone, or large, more complex circuits like using a 10-key touchpad for steering announcements to up to 999 zones. As we can see, Soundweb London Logic utilizes objects similar in appearance to the audio objects found in a Soundweb London DSP. They are placed into a user-defined order and wired just like the audio processing objects. Unlike the audio processing, which runs on the DSP, logic processing runs on the device's CPU, meaning it will not use any DSP resources. In fact, many Soundweb London devices that do not have any DSP do have logic, such as the Blue DA, Blue GPX, or any of the configurable I/O expanders such as the Blue 326DA and Blue 120. We'll find certain objects have control panels to interact with, while many others feature properties that must be configured for proper operation. We'll also see that logic object parameters can be linked to audio parameters for varying types of solutions. Now, what we use to build a logic circuit is all dependent upon what is required for an application. In this video, we'll look at quite a few of the available logic objects, and in part 2, we'll run through a few small simple examples to see how they can be used together. Let's jump into the Configure Logic section of a Soundweb London device. The layout is very similar to the Configure Audio section. We have our ribbon with several choices available, the Venue Explorer displaying the types of logic objects, and then we have the Workspace and Properties sections. We can select to simulate the logic so that the processes can be easily viewed while offline, and we also see a logic resource meter showing us worst case usage. When this meter is equal to 100%, approximately 50% of the host CPU is in use, meaning the logic should run without a problem. However, this is just an approximation. The resource meter does not factor in other CPU tasks such as parameter links or the number of control panels that are opened in Audio Architect communicating with the device. This meter can also exceed 100%, and we will still be allowed to load the device configuration. In part 2 of this overview, we'll take a look at the CPU usage when running a few examples in the logic configuration. Now let's take a look at common beginnings of a logic circuit. First, we find there are really 3 types of beginnings. Logic circuits can be driven using a binary parameter, a multi-state parameter, or a continuous parameter. An example of a logic object that supports a binary function is a logic source. Its control panel features, you guessed it, an on-off button. We'll find this is an extremely useful logic object as it can be linked to any other binary control such as a mute. We can take a shortcut when linking audio parameters to logic parameters. Simply control-drag the audio parameter directly onto the logic object itself. New parameter links will be placed into the Venue Explorer as they normally are. An example of a logic object that can be used for driving a circuit based on a multi-state parameter is the logic source select or logic value. Both are excellent choices for linking to an audio source select. One difference between the two is that the value can exclusively use the audio source selection of none as a source trigger, whereas the logic source select can be configured to allow none and ignore it, or not allow none and default to output 1 when none is selected from the audio source select. Here we see the difference between the two when linking them to the same source selector. And finally, for driving a logic circuit based on a continuous parameter such as a fader, the comparator is an excellent choice. We'll find there are many other useful beginnings, but let's move on to taking a look at some of the common endings of a logic circuit. The goal of any logic circuit is to trigger some type of event in response to the beginning or combination of multiple beginnings doing something earlier. There are 5 possible types of logic ends that can be used, and if you've already watched the parameter presets recall video, then you'll already know about the preset trigger. This object provides us with a total of 2 possible parameter presets that can be recalled. One for its low state and another for its high state. Or in other words, one for when it's off and another for when it's on. For larger requirements, a preset table can be used. It features a minimum of 2 inputs with a maximum of 12. With a total of 12 inputs, we have the possibility of triggering up to 4,096 parameter presets due to the possible combination of inputs that can be turned on. In simple terms, we could think of this as sort of a combination between a truth table and several preset triggers. The next common ending is the logic end. By default, it has 1 input, but a maximum of 32 inputs can be provided. It features a control panel with a text display showing the value of high inputs in binary -1. So that's 2 raised to the power of number of inputs -1. Looking at this from a smaller perspective with just a single input, this could be assigned to a general purpose output to drive an LED, it could be assigned to an LED on a custom control panel to relay info, or through its custom events properties, user-defined custom events could be specified and logged to the event log. There's even a neat way to reboot a Soundweb London device with the logic end. We'll take a look at that later. And finally, if we wish to control third-party devices using serial or IP commands, then we'll find we can make use of the serial and Ethernet trigger tables respectively. Both objects feature a property called mode of operation that can either be set to table or list. When in table mode, the object provides a total number of commands that can be sent to a third-party device equal to 2 raised to the power of number of inputs. So as an example, a serial or Ethernet trigger with 3 inputs can support a total of 8 commands. When in list mode, the object provides a total number of commands equal to 2 multiplied by the number of inputs. So that same object with 3 inputs now just supports a total of 6 commands that can be sent to a third-party device. Earlier it was mentioned that the goal of any logic circuit is to trigger an event based on the beginning or combination of multiple beginnings doing something earlier. Well, how do we combine multiple beginnings? One way is to use logic gates. A gate can take multiple inputs, and depending on the gate type and state of the inputs, the output of the gate will be high or low. In a Soundweb London processor, we'll find we have a few to choose from dependent upon the needs of the application. An AND gate, for example, will only allow the output to turn on if all inputs are on. So as we see here, using 2 logic sources to test, once this input is on and this input is on, then the output will be on. An OR gate's output will turn on as long as any input is on. So here we can see that if this input or this input is turned on, then the output will turn on. A NOT gate will invert the output based on the state of the input. So if the input is off, then the output will be on. Likewise, if the input is on, then the output will be off. And to round out gates, we find we have NAND gates and NOR gates. They are similar to NOT gates, however they factor in multiple inputs similar to the AND and OR gates. As we can see with the NAND gate, the output will only turn off as long as both inputs are on. All gates properties with the exception of the NOT gate can be configured to have a total of 32 inputs. To round out our overview of logic objects, let's look at some of the available logic processing objects. Here we see an example of a truth table with 2 inputs and 1 output. Using the properties, it has been configured to turn on the output as long as either input turns on, but will turn off the output if both inputs are on. We can think of a truth table as sort of a customizable gate. Next, we have 2 objects that can deal with time. They are the delay and time delay. They both essentially function the same way, but the way we enter time into each differs. Take, for instance, the time delay. It allows us to work with longer amounts of time by entering the value in as seconds. The delay allows us to enter time as multiplied by 100 milliseconds, or a tenth of a second. Let's look at the time delay since it'll be easier to see how it works. The delay on time has been configured for 2 seconds and the off time for 1 second. These times dictate the behavior of the output as it relates to the input. We can think of this as sort of a timed gate. This means that once the input of the time delay has been on for 2 seconds, then the output will turn on. The output will remain on as long as the input is held high. In order for the output to turn off, the input must be off for 1 second as it's configured. A delay object is great for, you guessed it, delaying an event from being triggered too early. Similar to the delay objects is the single pulse trigger. In addition to an on and off time multiplied by 100 milliseconds, we find a behavior option that dictates how the output will function. Here, the on time dictates how long the output will remain on, while the off time in conjunction with the behavior dictates when the output turns on. Let's illustrate each behavior simply using a logic source. Here we have the on time set to 3 seconds and the off time set to 2 seconds. With the behavior set to ignore input during pulse, this means that the output will turn on 3 seconds after the input turns on, regardless of whether the input reverts back to an off state before the on time has passed. If we change the behavior to restart pulse on low to high, then the output will take longer to turn on as the input continues to change states before the configured on time has passed. The third behavior of the single pulse trigger is to cancel the pulse on high to low. With this behavior set, then if we were to turn on the input and turn it off before 3 seconds has passed, then the output will fail to turn on. For the final processing objects in this overview, we have the counter trigger and the counter shifter. The counter trigger keeps count of how many times the input goes from low to high before turning on the output. A reset input is available to reset the count. Here, the logic source must be pressed twice before the output will turn on. Its auto off time has been set to a tenth of a second to minimize mouse clicks. The output of the logic source has been split into a single pulse trigger and its output has been wired to the reset. The single pulse trigger's properties dictate the logic source must be pressed twice before 2 seconds has passed in order for the counter trigger output to turn on. The counter shifter has the ability to turn on its outputs either in a binary format, or it can shift from one output to the next as it detects the input pulsing from low to high. This setting is found in its properties. A reset input is available to either turn all outputs off when the counter shifter is set to binary, or default to output 1 on when set to shift down. A direction input is available to subtract from the outputs when the counter shifter is set to binary, or shift up when the counter shifter is set to shift down. As we saw in the parameter preset recall video, the counter shifter was used to toggle among several different parameter presets using just a single button that was assigned to a Soundweb Contrio controller. This concludes our Part 1 overview. In Part 2, we'll look at building a few small examples and see how some of the other logic source objects can be utilized. Thanks for watching.